Uh, Hi everyone. Thanks for the organizers to organize this in-house. Uh, I'm Junaid and I will be talking about transport in ordered and disordered charged harmonic oscillator system in presence of magnetic field. So this work has been done with Gaitan Kane, Abhishek and Cedric Bernardin. Gaitan and Cedric are affiliated to University of Nice. Okay, let me just briefly give you the plan of the talk, what exactly I'm going to talk about. So I'll begin with heat transport in ordered chain after giving you motivation and introducing the system. And for this ordered chain, I'll try to derive the exact steady state solution and the expressions for the heat current in the thermodynamic limit. Here in the thermodynamic limit, I mean the size of the system goes to infinity. And later on, we'll consider this magnetic field to be disordered, and we'll study what will be the effect of the disorder on the heat transport. And it turns out that this particular system that we considered has very rich behavior with respect to the behavior of the current with the system size. So let me just introduce you the model quickly. It's a very simple one. So you have a bunch of oscillators, each having 2 degrees of freedom, X and Y. And the chain is 1D, and the Hamiltonian is basically given by the standard interacting Hamiltonian, where the interactions are x minus xn plus 1 minus xn whole square. So nearest neighbor interaction. And in order to study heat transport, we'll connect the reservoirs, we'll connect 2 reservoirs at the ends at some temperatures TL and TR. Okay, so this is basically the model that we'll consider. The reasons for studying such a system is basically this recent paper by Tamaki and others, where they studied heat transport in a similar system but in presence of interactions, and they find out that when you turn on the magnetic field, the thermal conductivity shows different behavior. So what we ask is in absence of the interactions. But for disordered magnetic field, what would be the power law of the current if there is any power law? By power law of the current, I mean how does the current scale with the system size? Okay, but in order to understand disordered things, disordered case first, one must understand ordered case properly. So that's why we'll first study the ordered case. Okay, from this Hamiltonian, you can directly write down the equation of motion, and it's an integrable system. So exact solutions are possible. So these are the equation of motion for the 2 degrees of freedom of the particle at n. So there are a few things I want you to note here. Note that the ends are connected with noise. Ends are connected with reservoirs, and the effect of the reservoirs is modeled by these terms eta L, eta R. X and Y refer to the 2 degrees of freedom, and there is a magnetic field which couples the velocities of the corresponding modes, corresponding degrees of freedom. And the exact solution basically looks like this, where G is the green function of the system, and this green function is basically given by these matrices with these elements. So K contains the magnetic field, and pi is the rest of pi contains the spring and the other things, the mass and other things. But there is one thing I want you to note here, which is this Cn. This Cn is 2 for all n for fixed boundary conditions, and it is 2 for all n except at the edges, except at the ends, means n equal to 1 and n equal to capital N. Capital N is the system size. So physically, these 2 boundary conditions mean so fixed boundary conditions physically would mean that the end particle here is connected to a wall with a spring. Okay, that I will refer to as fixed boundary condition, and free boundary conditions is basically this one. There's nothing after the end particle. Okay. So now finding the heat current from this steady state solution is pretty straightforward. You just need to find the dot product of the force delivered by one of the reservoirs on the corresponding end particle. And it is basically formally given by this. And once you plug in the steady state solution that you saw in the earlier slide, you basically end up with the expression for the current, which looks like this. So it's an integral over different frequency of this function T n of omega, which I'll call transmission. Transmission, because it is effectively the probability of a wave with energy, I mean with the of a wave with frequency omega being transmitted from one end to the other end of the chain. So that's why this is basically called transmission. So this transmission is given by this this function, which is once again from the steady state solution. So there are two contributing terms, the G1 and G2, which have their own physical interpretation. So G1 would mean you send in a wave at omega, which is polarized along x direction, and it would be transmitted as a wave on the other side, and this would be the transmission amplitude, and the polarization won't be changed. So G1 is basically the contribution from the transmission, so from the scattering process of the wave without the change in its polarization. And G2 is the contribution where the x disturbed wave will get transmitted as a y disturbed wave. So there will be a rotation of the polarization. So these are basically the two interpretations of these two contributions to the transmission. Okay, but these formulas, this G1, G2, these formulas are pretty hard and you can't make much progress by using these formulas. So there is another way in which you can rewrite these functions quite simply. Note that we only need one n component of the green function, which is basically reminiscent of the fact that only the edges are connected to the reservoirs. There is another way to obtain simpler versions of these two elements of the green function, which I'll just mention. I won't bore you with the details of that. So what you will do is take these, generate these numbers, small f and small g, and these are generated via this iteration equation using these boundary conditions. So you start with these boundary conditions and generate small f and small g. The plus minus, these iterations are basically same. The plus minus would mean the difference in the magnetic field sign in the iteration, and f and g is different initial conditions. Okay, so then once you have generated this iteration, if you want the transmission for a system size of capital N, then you calculate this fn plus minus of omega, which is a linear combination of f and g's. This capital F is then directly related to these two green functions components that we need for the transmission. And when you just put it there and just simplify a bit, you get this simple expression for the transmission. And it's very easy to like make analytical progress using these expressions. Okay, so this is for any special configuration of the magnetic field. So this will be useful for ordered as well as disordered cases. But now we'll study the thermodynamic limit of means n tending to infinity limit with b being constant, m being constant, and c for fixed. And c, as you know, it's essentially constant, except at the edges it's 1 for free boundary conditions. Otherwise, it's 2 for fixed boundary conditions. Okay, so when you take the thermodynamic limit, that's once again too much mathematical detail to mention, but I just wanted to show you the expressions. The expressions look like this. So there are two integrals in both of the both of the boundary conditions. First, the expression is different. So the boundary conditions matter even in the n going to infinity limit. And also there is an integral over two bands of frequencies, and we'll learn shortly why there is integral over these two bands of frequencies. That essentially means that at every other frequency the transmission is 0, because the integral over transmission has reduced to integral over these two bands of frequencies. Okay, just to show you how this expression in the thermodynamic limit for the transmission you can just read off the integrand of this integral. How this transmission compares with some finite size transmission. So here I am showing the transmission for system size of 20 compared with the thermodynamic limit transmission tau infinity of omega. So once again, you see the two bands, and the conduction is in the two bands. And you see at finite size, for finite size, there are sharp oscillations, and these oscillation peaks are exactly at the normal modes of the system. As I told you earlier, it's an integrable system and still a harmonic system. It has normal modes. So these oscillation frequencies are exactly at the normal modes of the system. And in the thermodynamic limit, these oscillations sort of average out to this blue curve, which is exactly the n tending to infinity limit. So this blue curve is the blue curve is the transmission in the thermodynamic limit. And while obtaining this transmission in the thermodynamic limit, that's exactly the argument one uses, that these oscillations will sort of average out to some mean value. Okay, so this is just a comparison. Now let's go ahead and some key points to note about this this expression for the thermodynamic limit of the current in the two boundary conditions in the thermodynamic limit. One is that there were two bands. That is basically due to if you look at the spectrum of the system, the normal modes of the system. There are two bands of normal modes of the system. That's why you see two bands, and the conduction happens only in that band. And these bands are gapped for EB greater than 2 MK, and therefore, so there will be a gap here between the two bands. If EB was less than 2 MK, they will overlap. The bands will overlap. Okay, now, the second and more important characteristic is that if you look at the transmission at low frequencies, if you take small omega limit of this, the current in the thermodynamic limit, you'll find out that the transmission goes as omega to the power 3/2 for B not equal to 0, and omega to the power 1/2 for B not equal to 0 for the fixed and free boundary conditions. So for fixed boundary conditions, it will go as omega to the power 3/2 for finite B, and for free boundary conditions, it will go as omega to the power 1/2 for finite B. This is in contrast with B equal to 0 case, where the transmission was known to follow the power laws with the small omega as omega square omega to the power 0. So this is something different. We found that once you introduce the magnetic field, the heat transmitted at low frequency is strongly modified, and this will also become relevant in when we study the disordered case, which is shortly after. So so please keep this in mind. So now let's look at the disordered case. Now let's ask that what if the magnetic field is disordered, what happens to the current? How does it scale with the system size? So transmission, for some general things, so in general transmission goes down if you introduce disorder in the system, but this system in other similar systems like mass disordered systems have this peculiar characteristics that the low frequency modes still end up contributing to the transmission. So as a result of this, instead of the current falling down exponentially with system size, it falls down as a power law. So normally you would expect the disorder will cause all the modes to localize, and therefore the current will go down exponentially with system size. But here the low lying modes would still contribute, and as a result of that, the current will go down with a less stronger form. It will go down as a power law. Now we'll learn shortly that why low lying modes will still end up contributing. Okay, so now I want to draw your attention to this plot. So as you can see that this is transmission plotted with omega for different system sizes. So there are three things to note from here. One is that there is a sharp cutoff after which it seems that the transmission is going down very sharp with the system size. And another thing that you may note is that below the sharp cutoff, the transmission is really independent of the system size. It's like staying the same. Okay. And the third thing, which is that below this this cutoff is basically somehow dependent on this size n. Okay. So keeping these things in mind, it seems that we can cut off our integral of the transmission. The heat was basically the integral of the transfer over all frequency. We'll just cut it off till some cutoff frequency, which will be a function of n. Okay. So we can assume a heuristic form of this transmission for the disordered case as this. So it will capture all of these details. So transmission will assume that it goes as omega to the power a e to the power minus lambda of omega n. So
Junaid,
when lambda,
Junaid, you only have less than a minute left, so please try to wrap.
Okay. So this lambda of omega n. So this lambda of omega, when this lambda of omega times n is an order 1 number, okay, then this omega to the power a will become relevant, and it will contribute. And when this omega to the lambda of omega times n will become much larger, then the transmission will basically be 0. So when you plug it in the transmission expression, you will just have to integrate the transmission over till this omega max n, where omega max n is basically the frequency at which lambda inverse of omega max n is basically n. Okay, and this lambda inverse of omega max n is essentially the localization length. So And this omega to the power a, we see that at low frequencies, the disorder really doesn't do much. So we just approximate this omega to the power a with the ordered case. Okay, so we basically need small omega expansion of lambda of omega. So it turns out that small omega expansion of lambda of omega can be obtained from the iteration equation itself. And I'll just show you the numerical results, although there is an interesting connection between the Lyapunov exponent of this thing and the Lyapunov exponent of a harmonic oscillator with a parametric noise. But just for this talk, the numerical evidence is enough. So it turns out that the lambda of omega, the Lyapunov exponent, behaves depends on the average of the magnetic field, and it goes as omega to the power 2/3 or omega to the power 1/2 or omega, depending on average b is greater than 0 and average b is less than 0 or average b equal to 0.
Junaid, your time is up, so please wrap up.
Okay, let me just sum up. Okay, so using this Lyapunov exponents and using the transmission behaviors that we learned from the ordered case, the current power laws are basically given by this. So the transmission at low frequencies is dependent on the magnetic field and the boundary conditions, and the Lyapunov exponent itself depends on the magnetic field. So we get 4 different regimes of power laws, and these are basically all the results. And when you verify all these results, and average b not equal to 0 turns out to be okay, but average b equal to 0 seems to have some problem. And when we looked at the problem basically was that our assumption that omega to the power a will just come from the ordered case is not as good as we thought. As you can see, that the transmission at the low frequencies basically is independent of whether it's ordered or disordered for b not equal to 0, but at low frequencies it is sensitive to still disorder. So let me just come to the conclusion. So the conclusion is all the things that I have mentioned because I'm running out of the time. So anyways, thank you.
Thank you, Junaid, for the talk. We'll entertain one question. Please go ahead.
So you have mentioned something about the localization length.
Yeah.
So it's in 2 dimension, this localization length?
It's the localization is
in particular
1D only.
1D.
Yeah, this is a 1D chain.
Okay.
Yeah.
And why particularly you have used magnetic field in this construction?
So it's because of this earlier paper, which seemed to have found very interesting behaviors of this thermal conductivity once we introduce magnetic field in presence of interactions. So we just removed the interaction and made the magnetic field disorder, and to see, because already there are analogous cases where mass is disordered and one sees power law behaviors of the current with system size.
Okay. Thank you.
Thank you, Junaid.